This is your review for electrostatics exam for physics. So the first thing we're going to look at is the summary for a helpful guide for electrostatics. So again, I'm just going to go through this. A solid object can have a net charge, could be net negative, net positive. If it's net negative, that means electrons have been added. Net positive means electrons have been removed. Protons aren't available to move. They are locked in place in solids. If there is no net charge, then that's what we call neutral. So neutral doesn't mean there aren't any charged objects. It means that there are equal number of positives and negatives. Two objects with net charge attract or repel. Unlike charges attract, like charges repel. Hopefully you already knew that. Charges could be transferred by rubbing, so friction, literally ripping off the charges. That's like if you're wearing slippers on carpet and you shuffle your feet, or by contact or touching. So if I have a charged object and I touch it to another object, some of that charge can transfer to the other object. Charge is conserved, so charge is another one of those things that cannot be created or destroyed. Net forces due to charges depends on amount of charge and distance, and then we found an equation for that. Of course, Coulomb's law will give us the actual relationships there. The forces of two charged objects on each other are third law pairs. So if you have two objects interacting, the force on 1 by 2 is the same magnitude as force on 2 by 1. The greater charge doesn't push harder on the smaller charge than the smaller charge pushes on the larger charge. Those are third law pairs. Just like the force of gravity on me is force of interaction between me and the earth doesn't pull any harder on me than I pull on the earth. The net charge on an object will freely move in a conductor. Metals are examples of conductors, so we make wire out of copper because it is a metal and charges are free to move along a conductor. Unable to move freely in a non-conductor or an insulator, like plastic, for instance. That doesn't mean that an insulator cannot become charged. It would just need to become charged by friction or by rubbing. If it's electrons that are the things that physically move, positive charges would be basically areas where electrons have been removed from it. Net charges would distribute evenly across the surface of a conductor. The charges repel each other, so any buildup of charges would get as far away from each other as they could, because due to repulsion that would minimize the repulsive forces between them, so they would spread out evenly across the surface of a conductor. If they're in contact, net charges would distribute proportionally across the surface of both conductors. So if I have a conductor touching a conductor, any extra charges would just spread evenly across both of them. Neutral charges are attracted to objects without any net charge. A positive would attract a neutral, but so would a negative. That's because the charges that are in the neutral object will redistribute or polarize. They would separate from each other, just like polar molecules in chemistry. If the neutral object is a conductor, the charges will move to the far or near limits of the object. If the neutral object is a non-conductor, then you only get a little bit of movement. A grounded object is one that free flow of unlimited charges in or out. And when we manipulate that, that's how we get an induced charge. And I'll show you that in just a second. So here's an example of two charges, a positive 1 and a positive 2. Those are unequal charges, and what we're going to do here is just draw the forces that those exert on each other. So there is a force on the plus 1 by the plus 2. There is also a force on the plus 2 by the plus 1, and those are equal in magnitude. They are opposite in direction. They are third law pairs. They have to be the same magnitude. The plus 2 doesn't push any harder on the plus 1 than the plus 1 pushes on the plus 2. Notice that these that are drawn here, those are force vectors. Those are not fields. That is not describing the field that those two objects create in the space around them. It's just discussing the force that they exert on each other. So if I have a neutral object, the charges would just be spread evenly. I've got two pluses, two minuses, two positives, two negatives. If I now bring a positively charged object near the neutral object, I still have two positives and two negatives on that charged object, but instead they would redistribute, and really, of course, you would have billions upon billions of each of those. This is just a simplified drawing. If I bring a positively charged object near the neutral object, then the positives would be repelled, the negatives would be attracted, and this is why you can use a charged object to pick up little bits of paper for instance. If you take a blown up balloon and you rub it on your hair, and you can use it to pick up little pieces of paper, or even a comb, get a plastic comb and run it through your hair a bunch of times. You can use it to pick up little pieces of paper, because charged objects attract neutral objects because of this separation of charge. So the charges separate, and then I have, well, the negative end of that little piece of paper would be attracted to the positively charged rod more strongly than the positive end would be repelled, because the negative end is closer. And as we know, distance has a big effect on the strength of forces. So if I have two identical conducting balls, they are made of a conducting material, so say metal, A and B, and they're attached to insulating stands. That just means that any charges are going to stay on the circle, stay on the sphere. The net charge on ball A is positive Q0. That just means it is positively charged, and there's no net charge on ball B. If I have a charged object near a neutral object, what's going to happen? Well, my charged object has some amount of positive charge on it, which would get distributed evenly on the surface. The charges on the neutral object, again, would separate, where the negatives would be attracted to the positively charged object, and you would get a separation of charge. If you just do another couple steps here, you would be able to permanently charge ball B. But in this particular case, ball B is only going to stay like that with the separation of charge when ball A is nearby. If I remove the charged object, then the charges on ball B would just spread evenly back out again. In other words, the charges are only polarized on B because the charged object is nearby. If I want to cause a permanent charge, then I would have to, if I want to charge by induction, I would have to follow the following procedure. First, I would just have a neutral sphere. I bring a positively charged object, for instance, nearby. That causes that separation of charge. So diagram 2 in this looks just like the ball A and ball B picture up above, right? You have a charged object near a neutral object causing a separation of charge. Step 3 then would say if you touch the backside of the charged of ball B, for instance, then we have a path for electrons to flow. In this particular case, electrons would come from the ground, right? The person is just a vehicle to connect to the ground, to cause even more electrons to go onto the neutral sphere. Diagram 4 says now you untouch the sphere, and leaving behind those extra electrons. Now take away the positively charged object, and you have now caused electrons to be permanently on that conducting sphere. So again, your steps are neutral, cause a separation of charge, ground, to allow electrons to either go from the ground into your object or from your object to the ground, depending on what situation you have. Then remove the ground, and then remove the charged object. So this is what I did in class with the electroscope, right? Cause a separation of charge, provide a path to the ground for any extra charges to flow, remove the path to the ground, remove the charged object, and you end up with a charged object. So this is the other way of causing that sphere to be charged. One way that we have is charging by rubbing or by friction, ripping electrons off. That's what we did with that's what we do when we shuffle our feet across the carpet, or if I have the acrylic rod and a piece of wool, right? You're literally ripping electrons off. This is the other way. This would be charging by induction, by causing a separation of charge and then a path for extras to go. So here's another couple situations. Here's two positively charged objects. Now this is not representing the forces that they exert on each other. This drawing is representing the electric field lines. The electric field lines take the place of drawing dozens of electric field vectors. They're mapping the space, is the way you want to think about electric field lines. They are describing the space around those positively, in this case, positively charged objects. If I now want to notice that the electric field lines, in this case, would go away from the positive, because we always draw electric field lines for a small positive test charge. If I want to know an electric field vector, I need to just take a look at what is the direction of the field lines at that location. And if it's in a curved section, then I would draw my electric field vector tangent to that curve. Electric field right in between those two equally charged, equal magnitude, positively charged objects is 0, because the electric field because of the left charge and the electric field influence because of the right charge would cancel each other out. We'd have one to the left, one to the right, equal magnitude, and they add to 0. If we were over at that location, again, we would use tangent. And then if we were at a location that was farther from the charged object, the field is weaker, so the vector is shorter. Also, at that farther location, the field lines are farther apart. Close together field lines means strong field. Far apart field lines means weak field. Here's another example. We have two charged parallel plates. One's positive, one's negative. We know that the field between them is uniform, meaning the same everywhere. So equally spaced field lines, and they're all pointing the same direction from the positive to the negative, because again, my small positive test charge would be repelled from the positive, attracted to the negative. So even if the plates weren't shown, you would know what plates must be there, because the small positive test charge would have to be repelled from the positive, attracted to the negative. If I now make those plates twice as charged, my field lines would have to be twice as close together. If I have more charge, the field twice the charge, you get twice the strength of the field, you'd have to have twice the density of field lines. In other words, they'd have to be even closer together, and ideally equally spaced throughout. If I wanted to know the direction of the electric field vector, direction and magnitude of the electric field vector at any location, it'd be absolutely identical. All three of those green arrows in the uniform electric field are completely the same. Whether I am testing a location that is on a field line or in between field lines, closer to the positive, closer to negative, it doesn't matter. For a uniform field, they are exactly equal everywhere. We have two equations that let us find the strength of the electric field. This is Coulomb's law, that it only tells us the magnitude. Neither of these equations that we have will tell us the direction. The direction has to come from your analysis of the charges and what you know the direction of the force would be. There is no positive means to the right or anything like that. Make sure you know the units that apply to all of those quantities. Here's our other way of calculating an electric force, and that would be if we know about the field. So we have two options. If we just have two charges interacting with each other and we know about what the charges are, you would use the first equation, Coulomb's law. If instead we know the strength of the field, then you would use that electric field is the strength of the field times Q. Again, make sure you know the units. The units for electric field are newtons per coulomb. If I have newtons per coulomb and I multiply that by coulombs, I'm going to be left with newtons, and that's the electric force. Hopefully those drawings are helpful. Good luck on your exam.